My name is Michael Wilson. I'm a medical physicist and I work in nuclear medicine and positron emission tomography. Medical imaging is just taking pictures of what's going on inside the body. Now we want everybody to see that, so there's a camera here. A typical medical physicist actually works in radiotherapy, and that's using radiation to treat cancer. Very often doctors need to know what's going on inside our body if they're going to work out what's wrong with somebody. The body's a fragile and wonderful machine, and seeing inside it can be quite tricky. But physicists are quite ingenious, and this lecture is about the ingenious ways that we've figured out to not only look inside the body, but see what it's doing and how we can help doctors make diagnoses that will make people better, hopefully. The lecture's called From X-rays to Antimatter, the Science of Seeing Inside Your Body. Thank you very much. My name's Michael Wilson and I'm a medical physicist, and I happen to work in something called nuclear medicine and in positron emission tomography. Now if that means absolutely nothing to you right now, then don't worry, because it's my job to try and explain some of that stuff over the course of the next few minutes or so. Because over the last 115 years or so, science has been building machines that will do what our eyes can't do, to see inside our bodies. And that's what this talk is all about. It's about the science of seeing inside our bodies. Now, why can't we see inside our bodies already? You may think the answer's really very obvious, because we see with visible light, and visible light just bounces off stuff. So since the light doesn't get inside us, we haven't got any chance of seeing inside us. That sounds perfectly reasonable, but it's actually not true. Let me see if I can show you that it isn't true. If we could have the lights down. I've got my bicycle light with me, ordinary red light, and if I try and cover it over with my hand, I think you'll agree that actually you can still see the light. It easily goes all the way through my hand. And that's a pretty neat trick that we can immediately put to quite some use. And before the lecture began, I asked James here to put a little gizmo on his finger. So James, if you'd like to come and show us what it is that you're wearing. This little gizmo is telling us some stuff about what's going on inside James's body. It's telling us that his heart rate here is 84, and we can see a trace of his heart beating at the bottom. And it's also telling us how much oxygen there is in his blood. It's telling us that he's at 98% of the maximum amount his blood will hold. And he's a pretty cool customer, because he's managing to keep his heart rate down at 86, whereas most people, as soon as they see it, starts to rush up. Thanks very much, James. You can take a seat now and take the gizmo off your finger. What's going on inside James's finger? Well, let's take a look. Basically, he's having some light blasted through. In fact, there are two different colours of light. One is red and one is infrared, so red that you actually can't see it. And both are absorbed by different amounts by oxygen in the blood. As the heart beats, so the oxygen in the arteries cause the amount of light that comes through his finger also to fluctuate. So we can immediately find out what his heart rate is. But the amount of light that's absorbed is different for both the red and the infrared. So by looking at the ratio of the different amounts of light, we can also figure out how much oxygen there is in his blood. Well, that's a neat trick, but it isn't actually imaging. We've got no picture of James's bones in his hand or muscles or anything like that. So why can't we use light to see inside the body when it does actually get inside the body? Well, let me see if I can explain how that is by showing you a little demo over here. What we've got here is a light, a lens, and a screen, and we've got an image of that light on our screen. And I've got some water here, which has just got a little bit of milk in it. So it's a little bit cloudy. It's like the stuff that our bodies is made of. So if I bung this in the light path, I hope you can see that there's still a fair bit of light getting to the screen, but suddenly we haven't got a picture anymore. And this is something that should be fairly familiar to all of you that have looked out on a foggy day. If you look out at this bridge, you can't see the far side of the bridge. Why not? Well, it's not because there's no light coming from it. This picture is very bright. There's loads of light coming from the far side of the bridge, but you can't see a picture of what's there because you only see the last thing that light bounces off. And in this case, it's the particles of water in the air. And when we bung some light inside our bodies, all that we see is the last thing that the light bounces off, and that's right at the surface. So we only end up seeing our skin. So what we need to see inside our bodies is something that will get inside but not bounce around and interact so much. About 115 years ago, this chap, Professor Wilhelm Röntgen, was playing around with things called cathode ray tubes. Cathode rays are produced when you take an empty glass tank, as we've got here, take all the air out, you put a whopping great big voltage across that tank, and something goes from the cathode, the negative electrode, to the anode, the positive electrode. 115 years ago, they had no idea what this was, but they called them cathode rays. And Röntgen knew that you could use these cathode rays to push a paddle wheel along, as you can see there. And he also knew that you could do things like bend them with a magnet. So some of you may still have a cathode ray tube in your house if you've got an old-fashioned TV. And if you take a magnet and you don't mind dispensing with the TV, you can bend the cathode rays as they hit the screen. And for those of you over in the corner there, you can see bending the cathode rays. So Röntgen knows quite a lot about these cathode rays, but he's about to discover something which is going to change the world. This is his lab, and in his lab he's got some photographic film knocking around in the corner somewhere. Photographic films are stuff that your mum and dad used to use in their cameras before they all went digital. And it's very sensitive to light, so he kept it wrapped up carefully so that no light could get to it. And he found when he started playing around with his cathode ray tubes that something like light seemed to get into the film through the covering. It didn't matter if he covered it in wood or even his own hand. Still, the cathode rays were producing some radiation that would get through to the film. When he put his hand in front of the film, he saw a picture like this. Actually, this is his wife's hand. The picture on the left shows the ring on her finger, and the picture on the right is a recreation, modern recreation. And you can see that the X-rays have a tougher job getting through the ring than they do through the bones, and a tougher job getting through the bones than they do the other softer bits of your body. So Röntgen has, almost by accident, found a way of seeing inside his own body. And when he publishes this, the world goes bananas. The world is totally gripped and fascinated by the idea that we can see inside our bodies with this new light. And everybody wants a piece of the action. Long before Brian Cox is the darling of science, Röntgen gets there first. He is the original scientific superhero. Röntgen makes his discovery just before Christmas in 1895, and just 6 weeks later, pretty much the whole Western world is starting to take pictures like this. A remarkably short period of time, and they're still used today, and they're still probably the commonest way that we have of seeing inside our bodies. So this is a cathode ray tube. This is where you put your photographic film, or today it would be something like you have in a digital camera instead. And the patient lies here. They're blasted with these mysterious X-rays that come from the cathode ray tube, and we create shadows of what's inside the body, not unlike this one. So this is the spine. The X-rays have a tough job getting through the spine, but not such a difficult job getting through the air of the lungs. And this bit of the lungs on the left here is filled with pus and all kinds of coagulating mess because this person has got a lung infection. Another reason that you might have an X-ray is to look at a broken bone. It's not strictly necessary to take this X-ray to diagnose that this person's broken their leg, because the bone is actually sticking out of the side of their leg, but it's quite a useful X-ray to have because look at all these bits and pieces. The surgeon certainly wants to know where they are so he can fish them out when he's doing a repair. You're going to have an X-ray at some time, I guess, when you go to the dentist, and the important thing I want you to see about this picture is that the fillings, they're metallic and they're very dense, and the X-rays have a really tough job getting through those. And we can use that to our advantage by filling the bits of our body which are otherwise fairly watery and difficult to see on an X-ray with metallic stuff. And here the large intestine has been filled with a dense material called barium. And we can use the same trick. Here we're using a dense material called iodine and injecting it into the arteries around the heart. When you get to my age, those arteries may start to fur up and narrow a little bit, and this is a great way to see any possible narrowing of those arteries. And I guess another reason that you're going to have an X-ray is because you've had an accident and you go to A&E, and again, not strictly necessary to take this X-ray to diagnose the problem. The patient has been stabbed in the eye, but you still do want to take an X-ray because when you pull that knife out, you do want to be sure it hasn't gone into, say, the patient's brain and they're going to bleed to death. So that's X-rays. They're still the most common way that we have of seeing inside our bodies, but they're not the only way. There are several others, and I want to tell you about those too. And the first one that I want to introduce to you is probably as different from X-rays as night is from day. So I'm going to illustrate that difference by showing you the difference between night and day. So here's the Earth, and over here we've got daytime, obviously over here we've got nighttime. Now, during daytime we see the Earth as we expect to see it on a map. We see pretty much what's there. That's like shining X-rays through our body. We see what's there. But at nighttime, well, we switch the light off. We expect to see nothing at all. But actually we see evidence of civilization on the Earth. The Earth emits its own light. What about if we could make our bodies emit their own X-rays? If we could do that, we might not get a picture of so much what's there, but what our bodies are doing. Well, it is possible to make our bodies emit X-rays, and the story of how we do that begins at about the same time that Roentgen discovers X-rays with this chap, Henri Becquerel. He was playing around with photographic film at about the same time that Roentgen was discovering X-rays. And he made the mistake of leaving some film in a drawer with a lump of rock. And he noticed that the film got fogged. He made a note of that, but he left all the details up to this feisty young lady from Poland. Her name, Marie Curie. She'd come to France at a time when women really weren't supposed to study at university at all. She blagged away into Becquerel's lab, and there she met and married Pierre Curie, and together they worked on this problem of the radiation from the rock. They called it radioactivity, and Marie Curie went on to win the Nobel Prize for isolating the element radium. Radium caused a stir just like X-rays had caused a stir. Everybody wanted a piece of the action. Everybody wanted to have radium on their brand. Everybody went bananas about radium, and it wasn't always for the right reasons. Radioactivity burst onto the scene, but it didn't find immediate use in medicine at all. And the reason? Because nobody really knew how it worked. Science at that point didn't really believe that atoms were real. And the first milestone is made by this guy, Ernest Rutherford, and he discovers that the atom has got a tiny really very small nucleus at its centre, and that nucleus is composed of protons and neutrons, and if you get the balance of protons and neutrons wrong, that's what makes things radioactive. So if we want to unbalance the nucleus at the centre of an atom, we need to shove in an extra proton or two. But that's tough. If you were to grab hold of a proton and stick it on the bottom of your shoe and try and push it into a nucleus, and we're just talking about one proton and any nucleus you happen to find lying around, you wouldn't be able to do it because the force of repulsion is too big. It would suspend you in midair. Of course, you can't do that. So we're going to have to wait a little bit longer before science finds a way to put a proton into a particle accelerator and give it enough oomph to get inside a nucleus. And that doesn't happen until the 1930s, when these two guys come along and build the first particle accelerator called a cyclotron, and it's a sort of early form of the Large Hadron Collider. And when this comes onto the scene, suddenly the world's able to make radioactivity for itself, and we're able to say, well, can we put this radioactivity inside people's bodies and see what comes out? Well, we can, but we need to be careful. And the reason we need to be careful is highlighted by this chap, Alexander Litvinenko. He was a KGB spy, you may remember 5 years or so ago, came to this country, and the KGB really didn't like that. So they decided to bump him off. One day he fell ill, a couple of days later he was in hospital, and he was really rather unwell. He died 3 weeks later, and nobody knew what was wrong with him. At autopsy, they found trace amounts of the element that Marie Curie had discovered 100 years before, radium. Just a few nanograms of that had been put into his tea and it killed him. So we need to be careful if we're going to put radioactivity inside our bodies. Now, some of you will know that radioactivity comes in different flavours. There's radioactivity that emits alpha particles, and they're what did this. We want to avoid that. There's radioactivity that emits particles called beta particles. It's just another name for an electron that comes spat out by the nucleus. And they're pretty dangerous too, so we pretty much want to avoid that for the same reason. There's radioactivity that emits gamma particles, and that's just another name for X-rays that come out of the nucleus. So those are the ones we want. We also want these radioactive materials not to be radioactive for too long. So that lessens the list of elements that we can choose. In fact, the list is really rather small. There are just 7 elements that are worth considering for injecting into the body. There are these 3, krypton, xenon and iodine. 2 of those are gases, so we could breathe those in. Iodine's quite useful. The body uses it to make certain hormones. So they're quite useful. Next on our list, this motley crew. Body's got no use for those whatsoever, but we're running out, so we've got to use some of those. Thallium happens to be, the one at the bottom, happens to be the most poisonous element in the periodic table. 1 gram, that will kill you. So we definitely don't use 1 gram, but we still use it. And last on the list, an element that didn't exist on planet Earth until the 1930s. Technetium turns out to be just about right, just about the perfect element for injecting into our bodies. There are lots of things wrong with it, but this is the element that we tend to choose to put inside the body. And in the 1950s, it was produced fairly cheaply, and also at the same time, this guy comes along, an American, and builds a camera that's able to see that radioactivity. So this is called a gamma camera. There are 2 cameras here. Let's strip away one of them. Let's focus in on the other one. And right at the heart of this camera is a very simple material. I've got a lump here. It's called sodium iodide. It's just like sodium chloride, the stuff you put on your fish and chips, except the chlorine's been replaced with iodine. So it's a pretty simple material. But the neat thing about this material is that when you shine X-rays on it, it gives off little flashes of light. So if we can see those flashes, we've got a hope of building an image of radioactivity in our bodies. And we do that by bolting some of these things onto the back of our crystal. And these are called photomultiplier tubes, and they're just very, very sensitive light detectors. But there's a bit of a problem. These things are huge. They're also quite expensive. If we were to build a picture by bolting an array of these on the back of a whopping great big crystal, then it might look something like this. So these are our light detectors. If we took a picture of somebody's face, it might look like that. we wouldn't be able to see any useful detail. Actually, we probably need to make these a bit smaller to see a bit more detail. These cost about 100 quid each, and they don't get any cheaper as you make them smaller. So that picture's costing us about, well, 64 of these, £6,500. If we double the number in each direction, suddenly we're spending £25,000 to get that picture, now 100,000, and so on. And before we've got a picture that we're really happy with, we've spent 25 million quid. So that's quite an expensive camera. We actually need to be a little bit more ingenious. We need to stick with detectors like this and hopefully end up with a picture like that. And to explain how we manage that, I've enlisted the help of Savian. Do your business there, and I'll explain what Savian's doing in a moment. And then I've got these four gentlemen. You know what you're doing as well. So if you'd like to take to the stage as well. So what we're going to do is recreate for you a light flash. We want you to see the light flash. So instead of particles of light, I'm using these plastic balls. Savion is providing the energy for our flash of light, and these four gentlemen are the very large and bulky, but quite sensitive detectors. Savion's putting all the energy in, he's nearly there, and when he's finished, we're just going to launch the flash of light and see how many particles each one of our super sensitive, but quite bulky detectors manages to take on. Thank you very much. A small round of applause for our muscular gentleman. So, gentlemen, are you ready? 3, 2, 1. So what I want you to do is quickly to count how many particles you detected in your detector, and I'll be asking for the results in just a moment. The gentleman over here, how many? 28, thank you very much. And over here? 25. And here? 7. And here? 20. So what we do is we allow our detectors to take a vote. And the proportion of light that they see determines where we think the light flash must have originated. So we've got these whopping great big detectors, but because they all use this sort of fair voting system, we can position the light flash quite accurately between them. So we've built ourselves a very sensitive light detector, but we're not quite there yet, because we've built ourselves a screen, and a screen by itself is not an imaging device. If I just see if I can illustrate that over here, back to our cross, here's my screen, it's very sensitive to light, but if I take away the lens, I haven't got a picture at all. What I need is some kind of lens that will focus the X-rays or the gamma rays from our patient's body. That's just what we see when we look at our own eyes. We need a lens in front of our retina. Anybody, any suggestions as to what we could use to focus X-rays? I'm not going to pass the microphone round, because if anybody comes up with an answer, please tell me and we will file a patent on it, because nobody's come up with anything that will focus X-rays. That's not to say it's not impossible. As far as we know, it's physically possible, but nobody's done it. Nobody's managed to do it technically. And there are real difficulties, obviously. So what we need to do is to replace our lens with something else. And what do we use? Well, it's a super high-tech piece of imaging equipment, not unlike this, a big bundle of straws. And if I try and show you how this works by going back to our screen with nothing in particular on it, and I move the source a bit closer so I can sandwich the straws in between, I hope you can see that we do get a picture of that cross. So this is our poor man's lens for X-rays, and that's what we have to use. So let's add that ingredient into our camera, and then we're finished. We've got ourselves a way of seeing X-rays that are coming from radioactivity inside our patient. So we turn this onto our patient and we see lots of little tiny flashes, each one a radioactive decay inside our patient. And if we build those up over a period of a few minutes, we get a picture something like this. Now, this particular radioactivity was designed to go into the patient's bones. And what it does is it shows us how the patient's bones are growing. So although this looks a bit like an X-ray, it's actually very different. And let me see if I can illustrate how it is different. So we've got 3 of these pictures. 2 of them are about my age, but 1 of them is about the age of these gentlemen over here. Right, who thinks that the teenager is A? Oh, we've got a couple there. B, couple more. C. Well, actually, the B's and C's were fairly good guesses. It isn't A, but it actually isn't C. And what's going on, if you look, let's say, at the knees on B, they're very bright here, but not so bright here. And actually, if you look at all the bones in this skeleton, they're all bright at the ends. And that's because these lads are still growing, and their bones grow from the ends. They pump bone into the middle. So that's a teenager in the middle, and that's me on the left. This poor guy has got bits of bone growing all over the place, in his ribs and in his shoulders, that really shouldn't be there. And unfortunately, that's a sign that a cancer, some cancer that's developed somewhere in his body, has spread and gone into his bones. So that's quite a bleak picture, but an important diagnosis. Let me just show you one other way that you can put radioactivity inside the bodies. You can put radioactive junk inside the body, and the body will try to get rid of it, and it uses the kidneys for that. So here we're injecting some radioactive junk. It gets sucked out of the blood by the kidneys, and we can follow it over a period of, say, 20 minutes. And this is a little movie sequence of that. And we can be fairly quantitative about this, so we can calculate some numbers. If I draw around the 2 kidneys, I can count how much radioactivity there is in each of these kidneys over the 20 minutes. And I think you can see that the left kidney sucks this radioactivity out of the blood and then sends it away into the bladder so that it can be gotten rid of when you go to the loo. Whereas the one on the right does exactly the same. It sucks this stuff out of the body, but it has a problem. It's got some kind of blockage, so it can't get rid of this urine so easily. So there's a problem with this right kidney, and that's an important thing to see, because the kidneys can function like this for a long time, but eventually that kidney is going to poison itself. That's a couple of ways of seeing inside our bodies, but I'm guessing that some of you are already thinking, hold on a second, if we watch TV programs like House or Casualty, very often the kind of pictures that you see there look more like this. They're not sort of 2-dimensional, they're slices through the body. We're seeing here the body in 3 dimensions by slicing it up like a loaf of bread. How on earth do we manage to do that? Isn't this all a bit too technical for you young minds? Surely I'm going to gloss over that. Well, no, I want to tell you how this is done, because actually this is quite simple to understand. And in order to understand it, I just want to tell you a couple of words. The first word is just the funny name that we use for slicing the body up like this. It's called tomography. It's got 2 parts to it. The first one, tomo, is a Greek word which means slice, or tomos, slice, and you probably know the word atom. Atom means can't slice, the thing that you can't carve up. So tomo means slice, and graphy is another Greek word which means to sketch or to doodle, or in this case, to make a picture. So tomography is a word that you'll hear a lot in medical imaging, and it just means slicing the body up, taking pictures of slices. Now the second word is a little bit more mathematical. It's a word that you know, it's called projection. This process that we need to understand is one of taking a 3-dimensional object and squishing it down flat. That process is called projection. So when we take an X-ray, the X-ray passes through the body, and everything along this line gets squished into this point. That's called taking a mathematical projection. What we want to do is to do the projection backwards. Now that may sound, well, how on earth can you do that? Well, about 100 years ago, this mathematician, Johannes Radon, he said you can do this, provided you take a whole bunch of these projections all the way around your patient that you want to see. And it was about 60 years later that this guy comes along, Godfrey Hounsfield, and wins the Nobel Prize for building a machine that would do just that. So let me just show you how that works by showing you what's inside a CT scanner. CT scanner looks like every other scanner you ever saw. It's a big white block with a hole in the middle. But inside a CT scanner is an X-ray source and some detector, and they just rotate around the body. And if we look at one in real life, it looks something like this. So it rotates quite a lot quicker than my animation. Okay, well, let's get on with the business of explaining what's going on inside one of these things when it builds pictures of slices. We're going to make life really easy for ourselves by taking the simplest object we can think of to put in our scanner. And we're going to choose a stick of rock because a stick of rock looks exactly the same. Doesn't matter how you slice it up, it looks the same at every slice. So let's make life a little bit more interesting by putting a mystery celebrity face inside our stick of rock, and let's put it inside the scanner. So we're taking now lots of X-rays as the scanner rotates, and we've got to figure out who this celebrity is from these X-rays. Well, since we got them by squishing all the information in the stick of rock together, let's unsquish them. Let's beam them back as if they were beams of light, and beam them back in the direction in which they were taken. And hopefully where those beams cross, that will give us information about the structure inside our scanner. So we'll add together all these beams as we go. So let's beam them back again, but we'll add them together as we go. And hopefully we start to see some kind of pattern emerging that gives us the celebrity that's sitting inside our stick of rock. But it's not very good. Anybody going to hazard a guess as to who we're looking at there? Cheryl Cole is our best guess so far. Cat from EastEnders. That's the first time that one's been suggested. Could you be right? Well, we've obviously got to do something to clean this picture up. We've got to find out what's gone wrong. Imagine that Cat from EastEnders has taken to wearing nose studs. So when we bung her in the X-ray machine, actually that's all we see. We just see a little blip on our scanner showing the very dense gold nose stud that she's wearing. So when we beam that image back, we just see all these little blips, and they all cross exactly where Kath's nose stud is. And that's the clue as to what's gone wrong. Because if we plot this out as a kind of mathematical function, sure, there's a big spike in the middle, but there's all this crud around the outside. And that's why our image looks so blurry. But now let's take 2 copies of this nose stud picture, just because we fancy it, and beam those back side by side. And now we build up a similar picture. It's got all the crud around the outside, but it's also got a hole in the middle. So now we've built ourselves 2 pictures, which are almost identical, but if we subtract one from the other, all the crud around the outside disappears, and just a blip in the middle is left. And that's Kath's nose stud. That's what we wanted. So what about if we use this trick for the whole image? Maybe we can discover who this celebrity is. Well, let's try it. So this is the original beaming back process, and this is the new fancy improved version. It was a valiant guess, but it is actually Angelina Jolie, who I don't think wears nose studs either, as far as I know. Anyhow, the important thing is that we can build up a slice picture. And if we can build up one slice, then we can build up more than one slice. And that means that we can stack them up in our computer memory. And that means that we can build a fully 3-dimensional model of what's going on inside our bodies. And that's great, because that gives us the opportunity to build all of those pictures that you see on television. We can colour those pictures in. We can render them with our graphics card. We can fly through them. In fact, we can truly see inside the human body. So I want you to remember one thing. First of all, you know how this is done. Secondly, the way to do it is to find a way of making one of those squished images. If you can do that, you can do this. If you can make a projection, you can do that. With that in mind, let's have a look at another couple of ways that we can see inside our bodies. Now, so far, we've been concentrating on one end of the electromagnetic spectrum. We've been looking at X-rays and at gamma rays. What other parts of the electromagnetic spectrum are useful to us? Well, ultraviolet and visible and infrared, we know they're not so good. Microwaves, well, they heat us up. But radio waves, we know we're reasonably transparent to those, so maybe we can use radio waves to look inside our bodies too. If we're going to do that, we need to make ourselves interact with them a bit. One way of doing that is to make ourselves a little bit magnetic. And if we're going to talk about how we make things magnetic, we need to talk about something called the X factor. Physicists have got this fancy thing which they call magnetic susceptibility, and they use the symbol X for it. And if you've got the X factor, then you're attracted to a magnet. And if you're not attracted to a magnet, then you haven't got the X factor. So there are no prizes for telling me which of these three materials has got the X factor. If I were to take a lump of steel, got a couple of lumps of steel here, and bring a magnet close, we know they're attracted. They've got the X factor. However, grapes and blue tack don't behave in the same way. They definitely haven't got the X factor. Their X factor is 0. Well, that's almost true. I've got some blue tack, I've got a grape, and I'm hopefully going to show you that if I bring this magnet close to the grape, it is actually magnetized. Here we go. Bring the magnet towards it, and the grape is pushed away. And the blue tack does the opposite. It's attracted. And I can try and slow it down and attract it this way. In fact, everything can be magnetized, even our bodies. They're magnetized because they've got charged particles that are spinning around in some way within that material. If we put our bodies inside a huge magnetic field, like the one you have in a scanner like this, let me just show you what's inside it. There's a huge electric current that flows around the outside of this thing, and it creates a whopping great big magnetic field. If you put your body inside that, you will become magnetic, partly because you contain spinning charges, some of which are protons, and they're the ones that interest us. And what we want to do is to start to play around with these protons and flip them so that they align and anti-align, they flip upside down inside our bodies, because that way they're going to tell us where they are. How do we do that? Well, actually it's quite tricky, because playing around with spinning things and trying to flip them over is harder than you might think. Let me see if I can show you the problem. Over here I have got a little spinning top. There's the spinning top. And it wants to be flipped over, and I'm going to move it close to the top of this huge magnet, and I hope you'll see it wants to flip over. But when I start spinning it, the story looks quite different. So I'm going to put it to the place where it wants to flip over. And now, because it's spinning, the magnet can't flip it over. It's doing the right thing, it's pushing in the right direction, but the spin stops it from being flipped over. So it has to hover there. If we want to flip over something that's spinning, we need to be a little bit more ingenious. Let me see if I can illustrate that. Stephen, this is your moment of glory. Come to the front, and if we could have the freely rotating chair, please, that's great. So in a moment, I'm going to give Stephen a spin in the form of this bicycle wheel, rescued from my wife's bike. She still hasn't noticed. I'm going to give Stephen this spinning object. Let's spin it up. Hold it above your head, like I said. And now let's try and knock it over. So put it down, and you can see that as he moves it down, he starts to move around. If you lift it up, Stephen, you'll stop. Move it down again, you'll start to spin around again. So if I was trying to knock over this spinning wheel, I'd have to wait until it came round, and I'd have to give it a knock. And then I'd have to wait till it came around again, and I'd have to give it another knock. In fact, I'd have to keep knocking at just the rate it likes to be hit at. And that's called matching its resonant frequency. Thanks, Stephen. You've done a sterling job. A small round of applause. And this process of hitting things at the frequency they like to be hit at is called resonance. This bar, for example, likes to be hit at a certain frequency so that it will oscillate this way. If I can hit it at that frequency, it will sing. I'll try and do it. How do I know what frequency to hit it at? Well, I don't have to. I just drag my hand across it, it starts to vibrate, and my hand ends up juddering at just the right frequency. And that's a trick that all you woodwind players know very well. You don't have to know what frequency to blow for a particular note. The rate at which the sound bounces off the bottom of the instrument determines the frequency with which your breath is interrupted. That's a shorter time scale and therefore a higher note. And I want you to think about the magnetization in our body as being like a sound coming from the body. So when we hit this magnetization, which is we'll think of as just a sort of an arrow pointing upwards, if we try and topple it over, we know it starts to spin round, but if we keep hitting it at the right frequency, it will go through this merry dance. And I want you to think of that as being the magnetization singing to us from the body. So we put our patient in the scanner, and we'll make different parts of the body sing at different notes by making the magnetic field stronger at the head than it is at the feet. So now we've got different parts of the body singing different notes. So we can get a signal from different slices within the body. If we just focus on one slice, we want to see the detail within that, we put another magnetic field that varies from left to right, and now these individual lines of magnetization start singing a chorus of different notes. And so we've built ourselves a way of squishing all the information in this slice into a series of points. That's called a projection. And we know what to do with a projection. We can build a 3D image from it. And we get images, beautiful images, from scanners like this called magnetic resonance imaging. This is a picture of the knee, shows wonderful detail around the joint there, the kind of picture that you want to take of a football injury. This is a picture of the arteries in the brain, here showing a brain tumour. And this is a picture of the heart, and you can even see the turbulence of the blood in the heart as it beats. I want to just tell you one other way that we can see inside our bodies. And that way is going to break the rule that I told you about earlier on. We're going to use radioactivity again, but this time we're going to inject one of those nasty flavours of radioactivity. I said gamma or X-rays were good, alpha was bad, and beta was bad. But actually, beta is not so bad, because some of these beta particles, which we know are just electrons, are not really electrons, they're anti-beta particles or anti-electrons. Some radioactive materials emit antimatter. And what happens when this antimatter meets matter? Well, something like this. They disappear. The two particles, the beta particle, the anti-beta particle, we call them an electron and a positron, they meet, they disappear, and what's left is a puff of energy, in fact in the form of two X-rays. And importantly, these X-rays come out along a line. What elements can we make radioactive in this way? Well, very, very happily, it's these. Carbon, nitrogen and oxygen are the very elements that we're made of. So if we can make those radioactive, we can see what our body does with those elements and all the molecules that we can make from them. So this could be a really powerful technique. How do we make pictures? Well, we build ourselves a scanner that looks a bit like this. It's just a ring of very small gamma cameras like the ones I showed you earlier, and they just detect flashes of light that come from the pairs of X-rays. But the important thing here is that the X-rays arrive in pairs, so each of these flashes has got a partner, and we can join the dots, join the partner flashes, and we get lines telling us that somewhere along these lines there are radioactive particles. So again, we've built ourselves a way of forming projections. I happen to have one of these scanners with me, or one that I've cobbled together from a scanner that was put on the tip. So over on the left side here we've got a segment of a scanner, on the right side the other segment. And I hope you can see, particularly if we bring the lights down please, that on the projection screen behind there are lots and lots of little flashes. Each one of those is a high energy particle being detected in one or other of these banks of detectors. And this pair of detectors is looking for two particles arriving at exactly the same time. It's looking for antimatter placed somewhere in here. Occasionally we do see a line joining two of these flashes. That's because cosmic rays are blasting us from the ceiling all the time, or from the sky, and occasionally a whopping great big shower hits this side at the same time as this side, and so we get a simultaneous flash. If I was to put some antimatter in here, we'd see a lot more. Well, fortunately, I have got some. Here it is. This is a very small radioactive source. It's sodium-22. It doesn't really like being sodium. It wants to get rid of some of its positive charge, and it does that by spitting out some antimatter. So if I put it in here, you can see that all of these lines point to where the antimatter is meeting matter and producing these puffs of gamma radiation, or X-rays actually, as they technically are. So we can track that around. That's how this technique works, and it's called positron emission tomography, because these antimatter particles are called positrons. We can make molecules like this radioactive in this way. This is glucose. We can replace one of the oxygens with a radioactive component. In this case we tend to use fluorine to replace the oxygen for biological reasons, and then we see how the body, or what the body does with glucose or sugar. And here's a picture. And the brain at the top of the picture there loves sugar. It uses about 20% of everything that we feed it. And the heart here sometimes likes to eat sugar because it's got a lot of work to do. And then all these other little bits, they really shouldn't be there, because the body really shouldn't be using that much sugar, and this is another way, an exquisitely sensitive way of picking up cancer, and in this case it's a fairly severe liver cancer. And we can pinpoint exactly where those cancers are by taking CT images at the same time and superimposing them, and therefore we can see exactly where those cancers are. I just want to say one more thing and leave you with one more image and one more question, and then I'm done. And the image is a picture of my own brain. It was taken 3 or 4 months ago, and these are slices through my brain. And whilst this picture was being taken, it was taken in one of those magnetic resonance imaging devices. I was asked to think about cycling. I was asked to think about cycling because I quite like cycling. And these little bits that you can see in red are the bits of my brain that I was using to think about cycling. Now the bits at the back here, they're all to do with seeing, because I had my eyes open. So I was using that bit of my brain to look around me. This little bit up here, and up here, and up here, and up here, that doesn't normally get used. That's called the premotor cortex, and it is used specifically to think about exercising. So this machine is actually able to tell what I'm thinking. It would be able to tell, to some extent, what you're thinking. If somebody is brain dead or thought to be brain dead, you can put them in a machine like this, you can talk to them, and even though they can't communicate in any other way, you can tell whether they're thinking about the right things. People have had their life support machines left on just because of a positive scan like this, because we believe there's a person in there somewhere. The question I want to leave you with is this. This century, the century that you're going to grow up in, has been called the century of the brain. Scientists have sort of set themselves the ambition of figuring out how the brain works, how it gives rise to what you call yourselves. The things that, like love and emotion and hate and envy, all of those things presumably come from this wonderful machine. So are you happy to be a machine? Or is there something else in there as well? Thanks very much for listening.